This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Well, hello, everybody, and welcome to the Math Map. I am going to share my screen here. Welcome to the Math Map Book Club. Today is February the 12th, and we are talking about Lesson 23, Matrices. This puts us our first of 4 lessons in 4D. So is that exciting, right? We're really going into a place where maybe we haven't thought too much before. So looking at our math map, we're here, right? Matrices, lesson 23. So we're winding down our year, and we are in the 4th dimension. And as each week, we are using the complex level as our base. And this is a great opportunity to address a question that we've had frequently recently, that we are working through complex. That's what we have said this book club is going to be about. But hopefully you've been encouraged each week that you can come with your digits, your naturals, or your fractions and use those. And this is true in community also. So next year, there's going to be several different levels, several different domains that are going to be available for our families to purchase and choose the domain that is going to best meet the needs of their homeschool and best meet the needs of their student. So next year, we're going to have digits, integers, fractions, complex, and monomials all available for purchase. Our Challenge A directors are going to be contracted to lead the complex domain. And our Challenge B tutors are going to be contracted to lead the monomials domain. And that's where their responsibility is for that particular domain. But students can bring any domain that they're using at home into class. So you may have a student who is working through fractions that comes to Challenge A, and their cover elements are the same. Their eye pages are the same. The only place that they're really going to see a difference in what you're working through in class is going to be those lesson pages. And even there, as we've seen before, those lesson pages are all mapped specifically so that the types of questions that students are working on in fractions are very similar to those that are being worked on in complex or monomials or digits, that those particular pieces of the page are going to look similar. So tutors don't need to worry about being prepared to teach or lead those learners through a different domain. They just need to focus on the domain that they have assigned to them for their particular level, and those students will be able to slot right in using whichever curriculum they're using at home. So hopefully that's helpful in answering that question. And that's just what we've been doing this year. Oops, skipped right over our mental math warm-up and doing it again. So here we go. We are still working through quick flip arithmetic. And I'm not sure exactly what Jill did with you last week. I know she was going to talk about positives and negatives, using your positive, your black cards as positive numbers and your red card as negative numbers. So I'm going to build on that this week and talk about how you could maybe take this game of the distributive property, and instead of flipping 3 cards, you could flip. Let me go ahead and make that change right here. All right. That you could actually flip 6 cards over and practice it with fractions, right? So there's a way that we can continue to take our quick flip arithmetic game and tailor that to the needs of our students. So if you have students who are perhaps struggling with fractions, right, you could choose to go ahead and practice your distributive property with fractions. So that's what I did here. I will be honest, because I wanted to make this something that would be easier for us to calculate and not have to make any changes to get like terms. I chose the denominator, right, to be 5, either positive or -5. And so that's something you could do at home. You could actually choose what you want your denominators to be in order to make those problems as simple or as challenging, right, depending on how much conversion between denominators you might need to do. So you can see here, what I did was I just flipped over my cards, and then I did them in pairs. So I had my 6 and my 5, 9 and 5, 7 and 5. And then again, we want to keep practicing, right? We're practicing the distributive property. So I'm going to practice, and right, we could help our students to remember that it's A times the quantity B plus C. Right? So if they don't remember, that's good to practice. And so I'm substituting in my fraction, my +6 over -5, my -9 over -5, my -7 over 5. Then I could read that. Now I went ahead and I simplified my negatives before I wrote what I was going to read. But I could read -6/5 times the quantity, 9/5 plus -7/5. Right. And I would encourage you, I think we've spoken about this before. We know that in foundation, students oftentimes say A opening parentheses, B plus C closing parentheses, because that's going to help them to see exactly what that form is. Reading this as A times the quantity, B plus C, is going to help them to see, I think, a little bit more what we're doing there in terms of the parentheses defining a quantity. I only wrote, just because the fractions take a lot of time to type in, I only put in the distributive property here as a way to do this. But certainly you could at home show that when we're dealing with numbers, we could have simplified our group first and then multiplied. And so here you see that the calculation is that first term, right? I'm going to use this one, my first term times my second term, plus my outside term, right, times my outside terms times the first, plus my outside term times the second. And so as I simplify those fractions, I see I have -12/25. Similarly, I could have simplified inside 9/5 minus 7/5 is 2/5 times 6/5 would give me the same -12/25. Right, so you could continue, if you're doing this numerically with your students, to emphasize that both using the distributive property and using our order of operations are going to give you the same answer. Now, in what we do next week, we're going to look at this with some reals or some imaginary numbers over the next couple of weeks. In other words, a sum inside, a quantity inside that cannot be simplified. And then we're going to see the power of the distributive property in that way. So we're going to continue to extend this idea of the distributive property and how we can practice that through different domains with quick flip arithmetic. So I know I talked a lot more here than I did asking you to warm up, but does anybody have any questions about what we did and this way of adapting that game?
I think sometimes I forget how complex you can get with the cards. Like instead of just like I just always think, oh, the cards I can just drill facts, but like that was really complex. Like something we really can dig into just with a deck of cards. So I'm glad that you like kind of showed how hard it can be. Like it doesn't always have to be just something like drilling your multiplication facts.
Yeah, I agree with that because I've had this book probably going on 10 years. And honestly, this is really about the first time I'm starting to use it. And I keep banging my head going, what the heck? Why have I not been using this? But it's great to see it model to us the complexity. The question I had, and this is probably, I think I'm on editing mode. Is that a typo under the calculate where you've got this -6/9 times 9/5 plus -6/5 times -7/5 equals -54/29.
Yeah, that would
Should
be
that
a
be
typo.
okay? Good. Whew.
Thanks,
'Cause,
thanks
I
for
don't
catching
trust
that.
myself. I'm so sorry, Kirsty. I don't mean to do that.
No, no, it's good. It's good. This is why there's a team of editors that have to go along after me and find all of, my errors, because what's in here is not always what comes out here. All right.
Oh yeah, I have the same problem. All right. Thanks for showing this to us because I just love it like Babs does.
Well, yay. All right. Any other questions or things to share? Yeah, and this is the thing, right? Is that it's a little bit more, I think it's a little bit more approachable for our students, isn't it? To like flip cards instead of a sheet of problems. And you really you can, and heck, let's face it, mom, if you're at home with your students, you can set those cards up to practice the facts that you know they need to practice even, right? So they might think this is a random flip of the deck, but you've gone through and set them up ahead of time. And something else that I was talking to somebody about today, I know one of the concerns sometimes for parents at home that a drill sheet might have an answer key, right? That makes it really easy. And when you're doing something like quick flip arithmetic, you maybe don't have an answer key. But one of the fun things that you can do, right, is if you're playing quick flip arithmetic with your students, is that they're doing the work, you have the calculator, and it becomes a beat the calculator game, right? Can they get to the point where they can calculate faster than you can put all of the things into your calculator? So, and now there's a lot of, even for fractions, because I know that sometimes even us as adults are a little reticent to deal with fractions. There's so many calculators now that will actually give you the answer in fractions, in fraction form. So for those moms that are maybe not as confident in their own calculation, that's just a little twist you could add to the game so that you're still checking their work, but in a fun way.
Okay, I do have another quick question, Kirsty. Am I forgetting a lot when I look at the -9 over -5, that somehow becomes a 9, just a plain 9/5?
Sure. So if you think what we could have written, we could talk about, right, negatives times negatives, or negatives divided by negatives become positive. But you could also see this as -1 times 9 and -1 times 5. And as soon as I have that -1 divided by -1, right, that becomes 1. So that's another way
Okay.
you could see that.
Okay, thank you. I knew there was something I wasn't seeing and forgetting about. Okay, thank you.
You're welcome. All right, well, let's go ahead and take a look at our cover and start our countdown so that it holds us accountable. Oh, I'm on the wrong screen. There we go. So what do you see this week? And if you don't know anything about matrices, what do you see in this art that might, what do you think matrices are based off of this art?
I don't understand them very well, but I do think of like layers of boxes. That's kind of what this picture looks like to me too.
This is very calming and peaceful to me. And I know some people would probably be like, what? But just the order and the symmetry and the way everything is lined up and correct, and there's light, and then you've got this definite dark line in the back. It's very peaceful.
I love what you just said about order and things lining up. those are some really great concepts to keep in mind when we talk about matrices.
Is it repeated patterns?
Okay, so we might see some patterns and some things that repeat. Any Latin scholars, what might be the singular of matrices?
Is it matrix?
It is. What does that word bring to mind?
Like measuring. I don't know if that's right, but I think like, I don't know. I'm thinking metrics.
It's similar. It's very similar, isn't it?
I was thinking Keanu Reeves was, was he
Same
the one?
thing.
That was
It
the
was
matrix
too.
I was thinking of too.
Well, what does matrix mean in terms of the movie?
Like another dimension, right? When they were in the Matrix, weren't they like in another dimension or another dimension might not be a good word.
Like an alternate reality or something.
I think the Latin word actually is the word they use for uterus. Isn't that right? Or am I making that up?
I have to go look it up now.
I never saw the movie.
I haven't either. I need to. I was thinking that as we started talking about this, I thought maybe I need to just finally sit down and watch the movie. Maybe we'll have a Math Map watch party. There we go.
Ooh, that would be fun. When they were viewing the Matrix, they were viewing the lineup of all the zeros and ones.
Okay, that's good. So this
For-
line up, going
Yeah,
back
for
to that
the
idea of organization.
So I Googled matrix, the etymology, and it says it comes from the Latin mater, which is mother. I'm trying to figure out how that fits this picture. Maybe because mothers are organized.
Or we try to be, right?
Right, we want to be. It's our goal.
If you're a Jimmy Buffett fan, there's a song, Mother, Mother Ocean. Like a pirate looks at 40, but the words are Mother, Mother Ocean. So now all I can think of is I can hear Jimmy Buffett singing Mother, Mother Matrix. So
My looking up also says that it meant womb or source or origin. So does that fit into anything mathematically?
that's really interesting. Well, as we talk about matrices, we'll have to think like, how does that root inform what we're thinking of? So if you think about like a womb or a place like a nursery of a bee, right? If you think of like a beehive where they're all the little compartments where the little bees are growing, that kind of looks like this picture, doesn't it?
Yeah, it really does.
I can't tell from the perspective if the vertical box, the vertical columns, if those are set upon each other or if they are offset.
Think they're offset, but I agree it's hard to tell. And this is actually, I think, a roof of a museum. So you almost have to pretend that you're lying on your back looking up at this. So let's take some of those ideas and let's go ahead and look at what matrices are. and move through our lesson, and then maybe come back and see if we can see where some of those ideas that we were thinking through, maybe it can inform us about mathematically what we're talking about. So before we jump into a matrix and the definition of a matrix, we need to take a minute and recognize that this is our first time in 4D. And so let's go ahead and start by defining hyperspace. So using what we have on our I squared page, our invention page, how would we define hyperspace?
It has infinite length, width, height, and breadth.
Did those terms feel familiar?
Yes. I think, wasn't it week 1? Week 1, we had like the dimensions and then characteristics of each one. And so that was one of the measurements, one of the lines.
When I read breadth, it made me think spiritual. It had such a spiritual quality to it. That's
Where
about
do
as
you-
deep as I can go.
Well, no, that's deep, because where do you think we got that word from?
God, the
From
Bible.
Romans.
The Bible,
Yeah.
yeah. So there's actually a verse, and I should have had it ready for you today, but there's actually a verse that talks about, right, knowing the lengths and widths and heights and breadths of God's love, right? And so
It's in
that's
Romans
why
8.
we chose that.
The one of the moms that's on here regularly that just has the best voice I've ever heard of recently said Romans 8. Who is that?
Thank you.
Jana, that's it. That is it. Yeah, she has a great voice.
Oh, you're
Great
awesome.
person. We love Jana.
You sound like a chain smoker right now. Thank you, guys. Yeah. Oh, and Pam is saying Ephesians 3:18. Okay. There's a couple places. My issue with the word breadth is that I want to think of it as like I have trouble thinking of it as a fourth dimension, but I like what you said about it making you think spiritually, because that helps me. Like if we say height and then depth, those could be the same, like the same dimension, if you will. Like you're measuring the up and the down, but it's actually the whole thing is one dimension. Does that make sense?
Yep.
And so I want to think like height and width and depth. It's hard for me to picture a fourth dimension. So I love that. I love that spiritual.
It's impossible for us in our 3 dimensions to think about the fourth dimension. Where does it go, right? Because just to review, right? So if I have my point and then I stretch that point, right? We're making an alignment, right? So I get my line. And so really that point, so if you think about, I've got a point, that point establishes our location, right? 0D, that as soon as I have a point, it's going to establish my location. That's my anchor for my entire coordinate system. But I can take my 1D line and it can intersect that point in any rotation, right? There's an infinite number of ways that I could say, here's my 1D. So let's pretend that I have my 1D this way, right? Because we're tempted to always think it has to be this way, but it doesn't. It can be any way, right? My first dimension can be in any rotation as long as it goes through that point. But once I have this rotation, this orientation of 1D, 2D has to go through that point and be perpendicular here. So no, I still have an infinite number of ways, but only around a circle, right? There's a circle, if you could think about that circle. And so there's my 2 dimensions, right? So now my 2 dimensions are fixed. And now I take and I go, okay, well, my 3rd dimension has to be perpendicular to both my first, right? and my second axis, well, there's only one possible way that it can be, right? So there's only one option for 3D in our 3D world. And now we say, okay, well, there's going to be a fourth dimension, right? We don't know. There is no way in 3 dimensions to put something at right angles to everything. All the slots are filled, right? So let's go back and think about, right? In 0D, right? All the slots are filled by the point. So I can't have a line until I get 1D, right? And then I say, okay, well, I could put it any of the ways that I want to. But in 1D now, right, the slot is filled. There's nothing that I can do in 1D that's perpendicular to this. There's just 1D. I have to have 2D in order to have that second axis. If I was in 2D, right, so think about your plane, in 2D, is there any way I can put another axis at right angles to them? No, right? Because if I go perpendicular to this axis, I get the other axis and vice versa. There's no other way without going, right, into 3D. And so we can't conceive of what that next dimension looks like because we're so firmly limited to our 3D existence, right? But somehow in 4D, I can have something else that comes in and is somehow perpendicular to all of these. But it happens in a fourth dimension, right? Now notice if I had, my fourth dimension out there, right? This might be my length, my width, and my height. I can call them anything I want, but let's pretend that we have our fourth dimension. Well, it might be that at this particular moment, I'm looking at my length, my width, and my breadth. And I don't see the height. Or maybe I'm looking at my length, my height, and my breadth. So I want us to understand that although we use this idea of length, width, height, and breadth to name these first, second, third, and fourth dimensional axes, right? I could be looking at any 3 at one time. I could be looking at any 2 at one time. So sometimes people will say, well, why does this say width times length? Sometimes it might say width times height. Well, because, right, I could be looking at any 2 dimensions, right, at a time, and pick those out and look at those, or any 3 of those. So I just wanted, right, I could be looking at dimensions 2 through 4, axes 2 through 4 in 3 dimensions, right? But if I'm looking at 3 dimensions, I can only see 3 of them at a time. So the big idea, right? And I want to encourage us with our students that might be like what you talk about all week, right? Is just imagining what might the fourth dimension look like. And you might not actually do a lot of calculation and math, right, in terms of checking off your lesson pages, because your students might be fascinated by this idea of what might that look like, right? And that may be okay, depending on your homeschool. So let's do a comparison question before we look at our Memoria page. Let's compare a space moved in time to an intersection of 2 spaces. Because there's going to be 2 different ways that we're going to think about the fourth dimension. And one of those is a space moved in time. Are we all moving? All the time? Right? Our Earth is rotating and revolving, right? So we are always in motion, right? And on the cellular level, we know we're always in motion, right? So even no matter how nice and still we're always moving. So again, you have to think in terms of this is where it's hard because we're tempted to take finite objects and say, okay, this represents 3D and it's moved, right? And so now I'm going to represent its position at time 0 and its position at time 2. And so we're kind of using a fourth dimension, a fourth measure, which is time, right, to talk about these two objects. And that's okay. But when we really want to think about what does that dimension look like, we have to stop and remember our 3D space is not finite, right? It's infinite, right? It's infinite. So in order for it to move, it can't move within itself in any meaningful way, right? In order for it to move, it has to move, right, into another dimension, right, through another dimension. And again, we can think about this because if I think about my my line, right, if I move it, right, it's infinite. If it moves within itself, we don't really see any movement, right, because it's infinite. It doesn't, it has no meaning really for it to move within itself. But if I want to see its movement, right, to a new location, then it has to somehow, let me use something that's almost the same color, right? It has to somehow move. And now notice, what do I need to describe that movement? I need a plane. So for a 1D infinite thing to move to a new location, it has to move within the plane. So if I took, right, my plane, my infinite plane, right, well, it's infinite, right? So for it to move to a new location, it can't just move within itself. It has to move to a new location. Ooh, made me disappear, right? It's got to move to a new location. And so in order to see that movement to a new location, it has to move in space. And then this is where it's hard because all of this has to happen in our heads, right? Infinite space to move to a new location. It has to happen in a fourth dimension, right? So there's one way we can think about what does that fourth dimension look like, right? Well, it somehow allows an infinite space to move to a new location. The other way we can think about it is thinking about, right, again, if I have 1D space, right, and it intersects another 1D space, right? Not so they're coincident and essentially the same, right? We're talking about non-coincident things. They intersect, right? As soon as they intersect, right, to see the intersection, I need a plane. I need a 2D space. Now I take my two planes, right? And if they're going to intersect with one another, right, what happens? Well, I have to have my 2D two 2D things that are intersecting. I have to see that in 3D. So now imagine that I've got two independent infinite 3D spaces. Right? Is that mind-blowing? Right? So here we can picture it. This is why looking at these patterns and dimensions helps us, because here we can see that these two infinite 2D spaces, right, can coexist in 3D. Right? So we know that there in 4D, there has to be the potential for there to be two separate three-dimensional infinite spaces. And if they intersect, then the only way that we could understand that intersection is 4D. Everybody having fun with these thoughts?
Yeah, and by that, there has to be an infinite number of dimensions, right?
Well, that's what we think, right? We think maybe there is. I don't know. I haven't been there.
It makes me think about how God is everywhere. And, you know, that's where your mind really starts to blow, because thinking about, yeah, these other dimensions and how God is everywhere, it's a lot.
And it is, because if you think about the plane, right? Right, that if this is me, hang on, right? This is me stuck in 2 dimensions, right? God can be all around me, right? On either side, right? So close to me, yet I'm completely unaware because I'm stuck in 2D, right? I mean, he could be, you know, as close as 2 numbers, right? But I don't know because I'm stuck in 2D. And so that's exactly right. When we think about, here we are stuck in 3D, but God is all around us. The heavenlies are all around us, right? When we hear, right, is it Paul that says, right, that children have these guardian angels who see the face of God? Because those angels can be all around them, even though they can't see them, right? They can somehow be in this other dimension with God, even though we don't see them.
So maybe would the 4th dimension be like the supernatural world?
It may be. So we don't, right? So there could be a physical 4th dimension. I mean, mathematically, this is when we talk about seeing the unseen. Mathematically, we can sit here and we can describe characteristics and properties of a 4th dimension. None of us can see that 4th dimension, right? Because we're in these 3. But we don't know how those other might intersect with ours, right? Although we do see, right, Jesus chose to intersect with our 3D and limit himself and have a physical form, yet he was still fully God, right? So maybe that gives us an idea of what that looks like, this intersection of spaces. But we don't know. But I think math helps us to think through what does it mean that God is all around us? What does it mean that the battles in the heavenlies are waging all around us and we're unaware? Right? It helps us to see we're not necessarily talking about heaven being some far off place, right? It gives us a way to start to interact with that and think through. And I don't ever want to claim that I have spiritual truth that is, right, unique, right? Any spiritual truth has to come from the Bible. And so, but I'm just saying that this gives us a way of visualizing it, right? Of going, maybe this is it. Maybe this is how or why, as we think through those things. So that's why I say these are some ideas that are big ideas, and you might be really surprised at your students and how they can grasp onto this and start using their imagination to see some things. And they may need to camp out on this idea, right? Or they may be like my daughter, you know, for a long time was just like, I don't want to think about that. Like, that's too big. Infinity and eternity are too big. And so maybe I want to really focus on, like, can I just do the math lesson pages this week and not think about the big ideas? But I think it's good for us to encourage our students to start thinking and playing with these ideas. All right.
If that conversation comes from the math lesson, I don't see how we can't be excited about that with our student. I mean, really.
So this page here actually is, so where our I² page was really emphasizing our 4th dimension, this page is emphasizing our matrices. And so here, right, there's a lot of things you could do. You could attend to the size of the matrices. And if you look at the top where it says dimensions, that's our size. And we measure the size in rows times columns. So we can go through and look at matrices and talk about how many rows and columns there are. There's things on here that you might want to memorize. The first thing to perhaps to memorize is the 2x2 definition of the determinant, because we've seen it now a couple of times as memory work in the math map, but now we're going to actually see where that comes from. You might want to use some expression. Some students may need help to remember, right, that rows are the horizontal and our columns are the vertical. So that might be a place to express, right, rows and columns. Even just remembering the order that we say that, rows and columns. I always remember that as RC Cola. So if you are somebody who has had RC Cola, that's how I always remembered what came first. Right. So those are some ideas for this page, right, with our students when they maybe don't even really know what a matrix is. That's some things that we could do on this page to practice those skills that form that art of memoria. So let's go ahead and take a look at our chart, and we'll talk a little bit more about what a matrix is. And so as you look at the chart here, you'll see that at the top, we're really emphasizing this idea of the 4D, right? And what does that mean to enter into the 4D? This piece in the middle, I just want to point out to you because we have a tendency to think about a linear equation and always think of it from a 2D perspective, right? So when we think about a linear equation, what do you think it graphs as in 2D?
That would be a line.
It would be a line. Yeah, it's a line in 2D, right? And so we're happy because lines are fairly straightforward in 2D. So in 2D, right? If I saw something like y equals mx plus b, we know that that graphs as a line. What are the exponents or the indices for the x and the y in this case?
One.
Just one.
One. Yep, it's that hidden one. And so linear, although it does mean that it's going to graph as a line in 2D, what it really is telling us is that it's a first degree equation, or that all the indices equal 1. So in 3D, if I rewrote this and I just said x plus y plus z equals some constant, right? And we could have had other things. Are all of my indices 1?
Yes.
Now, here's the trick question. In 3D, is that going to graph as a line?
No.
No.
It's not. Wouldn't it be nice if it did? And it doesn't, which is why we have that whole confusing vector equation, and we have to define lines as vectors because that's the only way we can do it in 3D. Because in 3D, a linear equation is actually going to define a plane or a 2D, right? So here it's a line or 1D. So when we look here, we're going to add another variable because we're in 4D. Let me change my color here to something that will show. So in 4D, I can add another variable. And it's not going to be a line. What do you think it's going to define?
Is it a cube?
Well, it would be a cube-ish thing, but it would be infinite, right? It's going to be a space. All right, it's going to be our 3D space.
Would it be like how it moves?
So if you think about, I'm trying to think how we can, right? So if I have 3 points, right, that defines, right, a plane, right? And so if I have, so when we look at our X, Y, Z, right, and this is why a stool is better than a 4-legged thing, because 3 points are exactly 1 plane, right? So as soon as I have my X, Y, Z, there's only 1 plane that they're going to rest on. So now if I add another point, right, another variable or another point, right, notice it's going to be a space, right? And so I'm going to see that that other point now, those are going to be together in defining this space. And that progression is going to continue. So if we were in 5D and I said X plus Y plus Z plus W plus V equals 5, what would they define? A 4D hyperspace, right? So my linear equation is always going to define a specific space that's sort of like one dimension down from wherever I am. And so that's what this piece here in the middle is all about. And the reason why I'm spending some time talking about that is because matrices are most commonly, not always, but most commonly, matrices are associated with linear equations. Okay, most commonly they're associated with linear equations. And the cool thing is that a matrix says, hey, if your equations all have the same variables, don't worry about the variables, just look at the numbers, right? So when you look at all of these examples that we have, not right, so there's examples here, and then we look over here at examples, notice that they're all numeric, which is why a lot of people like matrices, because it gets rid of all of those letters that just seek to confuse us, right? And so that's what we're going to practice this week, is arranging. So when we talked about order and arrangement and rows and columns, right? What we're talking about is arranging numbers specifically so that we can always know, usually, that each equation would be in a different row, and my first column is usually my X, and my second column would be my Y, and my third column would be my Z, right? And now I'm just taking the coefficients and I'm putting them in a matrix. And it lets me operate on them and simplifies a lot of the things that we can do. And so that's why there's actually a whole branch of mathematics called linear algebra that just studies linear equations and uses matrices to do so. And I say that because I want you to understand that we're dabbling in an idea here and introducing the grammar of an idea that, right, people that they dedicate their whole lives to studying. And so when you look at this, if you start to get overwhelmed or you start to go, well, why, or right, there's a reason why, because this is a dabbling and an introduction to the grammar of something that is really big and powerful, and worthy of life study. So you're not going to understand all of that this week.
I'm really glad that you just said that, Kirsty. It's making me think of the classical model in general. It's a really good picture of why we don't start with dialectic, but we learn all the pieces parts first, because I couldn't begin to work with this stuff right now. I just don't even have the basic building blocks, let alone try to explain it to my children. So I just love that this is such a good visual. And then you just said that, like, we're starting with just dabbling with, we're working with the grammar. We're learning the little pieces parts. And maybe next year I'll be able to be a little bit more dialectic with it. And maybe eventually I could even explain it to someone else.
Yeah, it's really important to remember, isn't it? There's a lot of grammar this week, right? There's a lot of grammar, right? So there's the 4D portion that we just talked about. These is like huge, big ideas. But then looking at the computation piece of this, the matrices, there's a lot of grammar. Now, when you look at the lesson pages, I just want to encourage you, when you're looking at the lesson pages, read the instructions, right? Read the instructions, do what the instructions say, and you're going to see that a lot of it is simple calculation that you're just kind of doing in context, but we're not asking you to necessarily understand, right, what's going on. So make sure you read the instructions and remember that we're dabbling in the grammar, we're building that base, and over time you're going to start to go, oh, I see some of the beauty here, I see some of the utility here. And then there's so much more, right? There's so much more beyond this. So some of you might have students who say, gosh, that's what I want to study. I want to go learn more about that, right? So, all right. So that's our charts. Does anybody have anything from last week? Any questions or testimonies they'd like to share?
I have a question on just how to read something in lesson 22. I was looking at it and going, I don't know even how to read that out loud. So one place is at the bottom of page 5, bottom left corner, copy the permutation equation. Could you tell me how to read that, please?
Sure. So 22, I'm going to make sure I look at the right page. So sometimes people will say pick for permutation and choose for combination. So here, I could say a permutation of n elements, k elements at a time, right? So that would be its kind of full name. I have a permutation of n elements, k elements at a time, or sometimes people will say n pick k. Okay, so there's the shorthand you might hear, but the full name would be a permutation of n elements, k elements at a time.
Thank
Which
you.
when we have numbers feels a little less clunky.
Yeah, I'm glad you asked that question. We actually have a flashcard that has that on it. Whenever I get to that flashcard, I get stuck. Like, what is my child supposed to say to me when they see this capital P with the little n and the k? And then on the back, it says equals n factorial over the quantity n minus k factorial.
Yes.
Is that how you read that?
That is how you read that. Yes.
Oh.
So yeah, so there, if I said I have a permutation, well, I would have to have said something. Let's do this. A permutation of 25 elements taken 6 elements at a time, or a permutation of 25 students taken 6 students at a time, right? And then the same for combination, right? I could have a combination of 25 students taken 6 students at a time, whatever it is that I'm looking at there. The important thing to remember there, and your students aren't going to get this year, and probably you aren't going to get this year, but I'm gonna give you the hint. If you look at the formulas, right, you have n factorial over n minus k factorial, and then here you have n factorial over n minus k factorial, and then I think it's k factorial. Which one is a bigger number? The P or the C?
Well, I think it's going to be the P because the C has a bigger denominator.
Yes.
Which, yeah.
Yeah, exactly, right? So P is a bigger number. And then we want to, when you think about this, and again, you're not going to see this probably this week, but over the course of years, hopefully, right, you're going to start to pick the grammar up, that the permutations says that order matters, right? So if I have 3 pens, right, order matters means that black pen, blue pen, pencil is different to blue pen, pencil, black pen, is different to pencil, blue pen, black pen, right? Permutation says that all of those different orders count. A combination says it doesn't matter what the order is, it's all the same.
Okay.
So does it make sense that there would be more permutations and combinations?
Yes.
Yes, right.
Thank you. That was helpful.
I will tell you that I love statistics. Probability is one of the most challenging areas of mathematics to study, right? Most people, the statistics is not what's hard. Most people, it's the probability that's hard. If you take a probability and statistics class, it's the probability that's hard. And it's because our brains really don't deal with probability well, right? We can conceptualize, heads and tails or rolling a die. But as soon as we start dealing with small or big or different combinations of things, we really have very little intuitive understanding, right? We as human beings have very little intuitive understanding of probability, right? So permutations and combinations are very common in probability because we're talking about what's the chance of getting something when I'm just looking at a few at a time. And it is hard to wrap your brain about that, right? And make intuitive sense. So if you're an intuitive learner, right, I think that especially for intuitive learners, probability is really challenging. So we only dabble in it here, but I just want to encourage you that if you look at the probability and it's challenging to you, there's a reason why, because it's challenging to most people. I would think challenging to just about every person.
Which is why they're able to sell so many lottery tickets.
Yes.
People don't realize how little chance they have.
It's true. It's really, really true. Yeah. Or going to casinos and, right, any type of gambling.
Yeah.
Yeah. All right, I'm going to just look at one page because you're going to see that I think these are similar and they're going to be focusing on the dimensional aspect, not the matrix aspect when we're looking down the sides for this one anyway. And so notice here we're looking at directions. So in 0D we have no direction. In 1D these are all cardinal directions. So remember, cardinal directions are fixed. They are not relative to you. So these are cardinal directions. So what would be the match to east?
West.
West. Yep. So we have west and we have east. What would be the match to south?
North.
North.
North. And so here we see we've got east, west, we've got south, we've got north. And then what would be the match to down?
Up.
Up. And then this is where it gets fun in 4D because we have these two words, Mart and Gart, that somebody made up and we're using them because they're the only ones out there. And it's like it's the cardinal equivalent of like an up towards and a down away. right? So we're going to see that there's these other words, ana and kata. Ana means up towards, kind of, and kata means down, away. But remember, it's a direction into that fourth dimension that we can't figure out where it goes because we can't be in the fourth dimension. So one of the things I would talk about with your students, though, here is that difference between a cardinal direction and a relative direction, right? Because a relative direction would be left and right, right? Forward and backward, right? It could still be up and down, although we even then tend to think up is a fairly fixed idea. So just understanding that some of our directions are relative to us and some are fixed is important to know. And so that's the difference between the relative directions and the cardinal directions. You're going to see here the next page, right, would be a point does exist in 0D, right? When we say to sketch, right, we're just talking about drawing a dot. We know that it's not really 0D. And then here we're just looking at some plotting practice. So -300 if our scale is 100 here. So 1, 2, 3. This would be -300. Plotting here, we're negative. Our scale now is 1 to 10. So that's going to be this point here. 15. And so one of the other questions that we've had is this whole idea of the orientation of the XYZ. And what I want you to see is that no matter how this is oriented, our positive X and our positive Y are going to be, right, whether I rotate it, however I turn it, my positive X and positive Y are going to be relatively the same. So if I was to rotate this whole picture so that the Y is going backwards and the X is looking horizontal, right, it's just a rotation because this space could be rotated anyway. Sometimes Lee just likes to put things so that it's in the front because she thinks that's easier for students to see. Sometimes in the back feels easier. But drawing it this way, the perspective just opens it up a little bit. So I would have parallel to my X15, right? Parallel to my Y. So I'm going to go parallel to my Y, parallel to my X, and then parallel to my Z. And I need to go up 15. And so here's my 15, 15, 15. And then because, right, again, we can't really do anything in 4D. So she just has us plotting the origin as being in the middle. So I think you're going to find that those side pieces and in fact, probably most of the lesson is going to feel more accessible than you think based off of the charts and the depth that we could go. I think Lee has done a good job of keeping those lesson pages pretty accessible. So don't forget, we've got all of our resources for our students and we want to continue to practice that. Lots of resources for you as parents. There's our upcoming book club dates as we move through the rest of 4D, and then March 11th, we'll be starting ND, our last 4 units. And that takes us to our time for questions. Does anybody have any questions?
Well, along with the question she asked about how to read the permutation formula, there's a few, I guess I just want maybe some tips other people have about working with flashcards. I know that Babs has been mastering the notations flashcards and maybe the fraction ones too. What I've noticed when we're going through them, if we come to a card like that one, the permutation one where I don't know how to read it, or there's one that's like, it has n over d, so numerator over denominator, and then there's the index is -m, and m is an element of n. Like I'm not sure how to read that, and so then we tend to just sort of put it aside and skip it, or maybe there's one that we don't know yet that's maybe a fraction or something. And I just wonder if you have tips for how to actually, I don't know. I'm going to stop talking and see if anybody has anything to say to me.
Well, I will tell you that we have talked about, and I don't know when it's going to happen. So like, hold this loosely. but as boring as it sounds, we have talked about like me literally going like through and just reading the flashcards. So kind of like the audio glossary.
Yeah,
Like,
I like that.
yeah. So boring, but perhaps helpful.
Yes,
Yes.
necessary. Yes.
So it'll become everybody's new sleep. Like, I need to go to sleep. Oh, I'll put that flashcard video on.
We can learn by osmosis as we dream. We can hear Kirsty teaching us math.
The other thing that you could do until we get that, right? I mean, so first of all, ask every week, right? We're here. Bring those questions and we can read those aloud, right, on the book club. So please feel free to bring those questions here. Alternatively, right, we don't always have to be verbal when we do flashcards, right?
Right.
We could have a whiteboard and say, okay, copy this. Okay, next time, see what you can do without me showing you the card, right? What do you remember? And just use a whiteboard to write those things down until you get to that point where you can write it on your own or say it out loud. Or if you wanted to play with just one or two flashcards, right? So flashcards doesn't necessarily always have to be a rapid drill, right? You could think, okay, how could we express this? So, hey, let's get spaghetti out and do some of these weird shapes or something like that. So there's different things that you could maybe do in that way so that you're still practicing it, even though it's not a verbal exercise.
Right. Yeah, that's good.
I feel like it's in levels too. Like I'll memorize one, like if there's 4 possible things that this letter could mean, right? The first time I'm going through, I'm only going to memorize the first one. And then as I get more familiar, I might pull that card back out and say, okay, now I'm going to try to do 2 meanings for that letter or that symbol or whatever it is. So I feel like I'm doing it in levels.
And do you just leave all of your cards like one direction and go through all of those and then flip them up? How do you, I'm being
I
kind
just
of,
do sections. Like I pick a section of maybe 10 to 12 cards and I just drill them every night until I feel like I know
okay.
enough about them that I would recognize them if I saw them, on a lesson page. And then I would put those 12 aside and then I would get a few more. And I just do them in little sections because it's overwhelming to have an entire deck for me.
Yeah.
So I just do them in little sections.
Yeah, I like that.
What we do too, and we usually do the front and the back. So we might not do 10 cards. We might only do 5 cards, but we are still getting 10 because we're doing the front and the back of them.
Yeah, because
That's
sometimes the
good.
side of one, I don't know, like sometimes one side is really easy, but the other side is like, I just can't get it. So you could camp out with 5 cards for a while if you're doing both sides.
I've started doing I do challenge 3, and at the beginning of class, I'll just do a few flashcards that I kind of quiz them on, and then the next week I add a few more. So I've been doing that. Actually, I've been doing that all year. But then when you get to one like function, it has this big long definition. And you know how for Andrew Pudawa, when we do the 3, I forget what it is now, I should know, but we do hand motions and I've sort of been doing that with like a function is a rule that maps each value, and then I'll just keep asking them throughout the strand. I'll like hold up the f of x card and say, what is this? And what is a function? And we all it's like we're doing memory work again, even though they're juniors, but that's been kind of fun. And I feel like it's, getting the stuff to stick too, so.
But Jana, I just want to piggyback what you just said, because you just said, even though they're juniors, we're doing memory work. Memory work never ends, right?
Right.
That foundations is not, this is all your memory work. And now
Right.
you graduate to a higher level of learning and you never need to memorize again, right? Foundations is, hey, we are training you in tools that you can use to memorize, right? So copy work, repetition, saying it out loud, moving your body, all of those strategies that our foundations tutors are modeling for the moms, and the moms are hopefully practicing at home, are the goal is that you take these tools and these strategies and you continue to use them throughout challenge in your life. so my daughter's taking kinesiology right now, right? And I said, well, are you using your skills to memorize, and sketching the muscles? And she goes, well, our teacher doesn't want us to memorize. And I was like, don't listen to your teacher, right? Because you cannot understand what something does if you don't know what the something is, right? There has to be some foundational grammar. And she goes, well, you're right. So we talked about what skills from foundations, right, can you use to help you memorize these muscle groups so that then you can understand how the muscles work, right? And so don't ever think that it's a bad thing to stop and practice memorization in any of our programs, because right, that's the foundation of all learning, is loading the grammar. So I think that's great, Jana, that you're modeling for those students different ways that they can load that grammar in. It did, and I'll just share this because, thinking about, with our students, the things that we want to practice over and over again, like going back and taking those skills, right? Say it 7 times, say it out loud, hear it, all of those things to help us memorize, even with our flashcards. But one of my very first homeschooling conventions that I went to, so we're talking like 2006, 2007, pre-CC days. And I think her name was Carol Barnier. She was sort of a homeschooling mom / comedian. And she said that, she made the joke. She said, well, we're homeschooling moms. And so you never get a moment. You go to the bathroom and your kids follow you in. So she said, I decided that was going to be a useful time. And I started keeping a whiteboard in the bathroom. And when they came in, I'd say, great, we're going to practice spelling. So
my kids are juniors and they still follow me into the bathroom.
So there you go.
Sorry.
So you just need to stash a few flashcards in each bathroom. And when they come in, you just go, great, let's practice our flashcards.
You're finally
I
here.
love
I've
it.
got some flashcards for you.
Jen,
That's great.
there was I don't know if she was a 3 or 4 director, that she was trying to schedule a competition with the Challenge A kids and her class, because she was drilling the flashcards. Challenge A kids were drilling the flashcards, and they were going to have a competition to see who could remember the most flashcards.
That's a great idea.
The older ones don't want to be shown up by the younger ones, so it would be very interesting to see how
It would and the younger ones would love to show up the older ones. So it would be motivating in both directions. Yeah, that's great. And thank you for reviewing that very basic classical education pedagogy. Like that, it's so true, Kirsty. I don't know, I forget it sometimes, but grammar, hammer it in there, and it makes everything else so much
not
easier.
Really fun. We like the dialectic moments. The grammar loading doesn't always feel like fun, right? And so remembering that that's essential is important.
Yeah.
I have a question. Back in booklet 19, I was working on the bottom half of page 8, and I was just struggling to find the pattern. So on the bottom half of that page, for instance, if I look in that second row where it's -4, 60 degrees, and then 60 degrees, I could figure out where to put them then in that next box with the x equals, but then I struggled on the equation below that. And I was hoping my chart 4 would help me, but I looked on chart 4 and I still couldn't find clarity or direction.
Sure. So I'm guessing. So let's look at the second row.
Okay.
I am gonna actually stop sharing this screen and share a different screen that should work better. So can you guys see the pink screen?
Yes.
Okay. So let me Sorry. Okay, so we're given here -4, 60, 60. And then we have x equals blank cosine blank sine blank. And so then what we're going to plug in here is our -4, our 60, and our 60. And below that, my -4 stays the same, but what we're going to put in here is literally the cosine of 60. And so the cosine of 60, right? So here you go. I have not memorized this, right? So I always have to draw my picture. So this is my 30, 60, 90. This is 1, 1/2, and this is the square root of 3/2. So my cosine of 60 is the square root of 3/2. And my sine of 60 is, oh no, I just lied to you. I got them backwards. My cosine of 60 is 1/2, because it's my adjacent. My sine of 60 is the opposite. That's the square root of 3/2. And that's as far as I need to go. But eventually, right, if I was actually completing the conversion, I would multiply this through and end up with negative square root of 3. So then my y coordinate is blank sine blank sine blank. And so now my -4 in the place of r, then my 60 and my 60, -4. So my sine of 60, that's my opposite, that's my square root of 3/2. My sine of 60, doing them both, right, is the same, square root of 3/2. And then my z is blank cosine blank, and we may need to look above and see that that's phi, that's my third angle. And so my radius is still -4. This is 60. And so this becomes -4 times 1/2.
So I guess, so we need to remember that sine means opposite and cosine means adjacent. So if we come to this page and we don't have that, I guess that's where it's challenging to know.
It is, because that's where you're going to have to go, okay, wait, I've got to jump back to 16 where all of those things were defined.
Okay.
16. Yeah.
Okay.
Yeah, after we hit, I mean, you see it before lesson 16, but after we hit lesson 16, you're going to start seeing, you know, that we're going to be using those more, and assuming that we know people don't really remember, right? But that's what you would go back to, is lesson 16 to review those.
Okay, that's helpful. Thank you.
Any other questions? Well, I hope you all enjoy thinking deep thoughts about the fourth dimension this week, and also enjoy calculations that shouldn't be too challenging, because we're looking at the form of them, not the calculation themselves. So, and I will look forward to seeing you all back next week when we talk about rates, movement, and time. Have a great week.
Thank you very much, as always.
Yes, thank you.
Well, thank you all for being here.